Hi, welcome back. This is section 6.2. We're going to talk about geometric sequences. So in this video we are going to talk about how to write a geometric sequence using an explicit or recursive formula to model a real-world context, how to write a recursive formula using an explicit formula, and vice versa, and then how to write an explicit function, define a recursive process, or complete a table of calculations that can be used to mathematically define a real-world context. So let's take a look at these three numbers right here. So when we graph them, we notice that they are certainly not in a linear pattern. The rate of change to go from one to the next changes drastically. And so if we mathematically want to find the relationship between 2/5, 2, and 10, we want to think to ourselves, well, what operation gets us from 2/5 to 2? And then from 2 to 10. And it's fairly obvious that we're not going to be adding by the same thing, because when we look at the graph, our rate of change is not the same from one point to the next. So let's take a look at multiplication. So is there a number x, let's say, that we can multiply to 2/5 to get 2? And in that same idea, is there that same number x then we can multiply to 2 to get 10? Well, the second question is probably easier to answer. So if we solve for x, we divide by 2, and so x equals 5. And so here, if we multiply 2 by 5, we get 10. And so the question is, and that's multiplication, not raised to a power, can we do the same thing to 2/5? Can we multiply 2/5 by 5? So that is, can we put 5 here and get 2? And in fact, that's what happens, because 5 divided by 5 is 1, and so 2 equals 2. And so that is the definition and the beginning of geometric sequences. So in a geometric sequence, rather than adding by a constant amount, we are going to multiply by a fixed amount that we call the common ratio. Remember, a ratio is just a fraction. It's one number over the other. And that ratio is found from taking any term and putting it over its preceding term. So, for example, if we take 6 and divide by 3, we get 2. If we take 12 and divide by 6, we also get 2. If we take 24 and divide by 12, we get 2. If we take 48 and we divide by 24, we get 2. And so this is actually a geometric series because you're going to multiply by 2 to get to the next term. Let's take a look at this example. This is 3 to the 5th, 3 to the 10th, 3 to the 15th, and 3 to the 20th. Well, it might be a little bit more difficult to be intuitive about how you go from one to the next. Like here, 3 to get to 6, that's fairly simple to see too. This might be a little bit more difficult. So let's look at how we could go backwards. That is, how could we go from 6 to 3? Well, again, we can do 6 divided by 3, and that gave us 2. And we could do that with every single term going backwards. Well, for this, we could do the same thing. So let's do 3/10 divided by 3/5. Well, this is just the properties of exponents. So 3 to the 10 divided by 3 to the 5th is 3 to the 10th minus 5, which is 3 to the 5th. And so we can test out 3 to the 15th divided by 3 to the 10th is 3 to the 5th. 3 to the 20th divided by 3 to the 15th is 3 to the 5th. And so this is indeed a geometric sequence because we're multiplying each term by 3 to the 5th. How about this one? Again, so 6 divided by 3 is 2, but 9 divided by 6, that is not 2. That's 3/2. So this is not a geometric sequence. How about this one? Pause the video. Okay, welcome back. Well, let's test. 5 divided by 1, well, that's 5. 9 divided by 5, though, that is certainly not 5. So this is not a geometric sequence. Let's try this one. Well, 27 divided by 81 is 1/3. And 9 divided by 27 is 1/3. 3 divided by 9 is 1/3. and 1 divided by 3 is also 1/3. So this is a geometric sequence where we're multiplying each term by 1/3. Let's try one more. Go ahead and pause the video and see if this is a geometric sequence. Okay, so we notice that 10 divided by 100 is 1/10, 1 divided by 10 is 1/10, 1/10 divided by 1 is 1/10, and so this is a geometric sequence because we're multiplying each term by 1/10. We can use this to find missing terms because we know that to go from 3 to this term right here, we're going to multiply by r. And then to go from this term to this term, we're also going to multiply by r. So that is, we're going to take the number 3 and we're going to multiply by r, and then we're going to multiply by r again, and we should get 12. So if we simplify this, r times r is r squared. We end up with 3r squared equals 12. If you divide by 3 on both sides, r squared equals 4. And we remember from radicals unit, if we take the square root of both sides, we're going to end up with r equals positive or negative 2. That is, both positive and negative 2 square to get positive 4. So which common ratio gives us this middle term? And the answer is both of them, because we don't know. Unless we know something else about the sequence, or we know what the real world context is, it could be either positive 2 or negative 2. We're not sure. So regardless, 3 times 2 is 6, and so 3 times positive 2 would be positive 6, and 3 times negative 2 would give us negative 6. So our missing term is positive or negative 6. And we can do this with any number of terms. So 10 times r times r times r equals 80. So that is 10 times r cubed equals 80. Which means r cubed has to equal 8 if we divide both sides by 8. And now if we take the cube root, r equals 2, and we know that cubes maintain their sign, so the cube root of r has only one root, it's 2. And so if r is 2, then to go back to this problem, 10 times 2 is 20, and 20 times 2 is 40, and just to double check to make sure it works out, 40 times 2 is 80, and so our missing terms are 20 and 40. Okay, go ahead and try, this is C, go ahead and try C and D. Okay, welcome back. Here are your answers, C and D. Let's explore the relationship between the terms in the geometric sequence a little bit further. So we notice that immediately 2 and negative 6 have a ratio of negative 3. So we know the common ratio here is negative 3. But there's a little bit more to the relationship between some of these terms. In fact, if we look at non-consecutive terms, and we look at multiplying them, because geometric series deal with the multiplication, we notice that 2 times 18 is 36. And 36 has a direct relationship with negative 6, the term that's in between 2 and 18. Specifically, 36 is the square of negative 6. And in fact, this happens for any two non-consecutive terms, because negative 6 times negative 54 is 324. 324 is a perfect square of 18 squared. And so this concept where if we take the square root of the product of two numbers, we get what's called the geometric mean. So that is the value that is in between those two numbers in a geometric series. Let's take a look at an example. So in this example, we want to find the geometric mean of 2/5 and 8/45, which sounds at first like it's going to be fairly complicated. So let's try using the geometric mean, which remember is the square root of xy, or the square root of the two non-consecutive terms. So we're going to take the square root of 2/5 times 8/45. Well, in the square root, then we have the square root of 16 over 5 times 45, which is 225. And then radical rules tell us we can take the square root of 16, and then we can take the square root of 225, which gives us 4/15. And since we're taking the square root, we have to consider that it could be positive or negative 4/15. So our geometric mean is positive or negative 4/15. Go ahead and try this one on your own if you think you're ready. Okay, welcome back. So geometric mean again says the square root of these two numbers multiplied together. So 1 times 1/4 is the square root of 1/4, and the square root of 1/4 is 1/2. So the geometric mean is positive or negative 1/2. Go ahead and try this one. Okay, welcome back. So here are our answers. So when we're looking at a geometric sequence, we notice that the common ratio, r, here is 2. So is there a way to write this in a formula so that we don't have to list out all of the numbers? Well, if we number each term, so that is 3 is the first term, and 48 is the fifth term, and this is going to go on forever because we could multiply the numbers by 2 forever and ever and ever. So by that definition, to get to the next term, we're going to multiply by the common ratio. So we take the term, to get the term, so to get a of 2, we take the previous term, which is a sub 1, and multiply it by 2, the common ratio. So we're going to take each one and multiply by 2. But we need to know where to start, right? Because we can't just start multiplying nothing by 2. That won't get us anywhere. So we always have to know our starting point, a sub 1. So in this case, a sub 1 equals 3, because that's our starting place. So formally, the recursive definition is always the first term. So a sub 1 equals a, some number a. And to get each following term, we're going to take the previous term, which we denote a sub n minus 1. That's how we say that, which basically means the term before it, right? 5 minus 1 is 4. 4 is before 5. Times the common ratio, which is r. Okay, so let's write the recursive definition and find the next term in the sequence. So finding the first term is fairly easy, especially here when it's listed out for you. So the first term here, a sub 1, so a sub 1 equals 4. Finding the common ratio, a little bit more work, but just as simple. So we're going to take the second term and divide it by the first term. So 12 divided by 4 is 3. And to check to make sure this is a geometric sequence, we can do 36 divided by 12, and we better get the same thing. And 36 divided by 12, and in fact we do get 3. So that means our common ratio is 3. So we can write out our formula. A sub n is the previous term, a sub n minus 1, times, so you can use the multiplication symbol, 3, where a sub 1 equals 4. And so to get to our next term, so this is a sub 1, a sub 2, a sub 3. So to get a sub 4, we're going to multiply a sub 3 times 3, which is 108. So a sub 4 is 108. Okay, let's try this one. So again, we need our starting point, which is 2 to the third. So a sub 1 equals 2 to the third. And then to get our common ratio, we're going to take the second term and divide it by the first term. So 2/7 divided by 2/3 is 2/4. And just to double check, the third term, 2/11 divided by the second term, 2/7 is also 2 to the 4th. So we know that the common ratio is 2 to the 4th. And so the recursive formula is going to be a sub n equals the previous term, right, the one before it, a sub n minus 1, times, I'm going to use parentheses this time. It doesn't really matter. You can use parentheses or you can use the little circle. It's up to you. Where a sub 1 has to be 2 to the third. And to get my next term, I'm going to multiply 2 to the 11th by 2 to the 4th. So to get my next term, I'm going to multiply 2 to the 11th times 2 to the 4th, which means I have 2 to the 11 plus 4, which is 2 to the 15th. So my next term, which is a sub 1, a sub 2, a sub 3, a sub 4, is 2 to the 15th. Okay, let's do one more. So again, always find your first term. So a sub 1 here is 1/10. And then I need my common ratio. So I'm going to take the second term, negative 2/10, and divide that by the first term, which is 1/10, and that gives me negative 2. And then I'm going to multiply the third term by the second term, just to double check and make sure my ratio holds, and that is also negative 2. And so negative 2 times 4/10 is negative 8/10, so indeed my common ratio is negative 2. So my recursive formula, any term is equal to the term before it times the common ratio of negative 2, where the first term is always 1/10 in this problem. And so to get my next term, so a sub 1, a sub 2, a sub 3, a sub 4, a sub 5, I multiply negative 8/10 by negative 2, and I get positive 1.6. Okay, go ahead and try these on your own. Pause the video. Okay, welcome back. Here are your answers. So just like we did with arithmetic sequences, we have a recursive definition, and we can rewrite the recursive definition into an explicit definition. So our explicit definition is very similar to something you're going to learn about when we get back from break. So it's going to be a sub n is the first term times the common ratio n minus 1 number of times. Okay, so if we're at the first term, we just have the first term. So we're going to have n minus 1, which is 0. Anything to the 0 power is 1. And so as we go up, we get more and more r's that are being multiplied together. So a sub 1 times r to the n minus 1. So let's use that to write the explicit definition for this same sequence that we just did. So we already know r, right, is 3. So if r is 3, and we're given a here is 4, which we know from the sequence, so a sub 1 equals 4, we can rewrite this to say a sub n equals a, which is 4, times 3 to the, in parentheses, n minus 1. And so we can find the ninth term, so a sub 9 equals 4 times 3 to the 9 minus 1, which is of course 8. So 4 times 3 to the 8th power is going to be 6,561. 1 times 4 is 26,244. So a sub 9 equals 26,244. Let's try another one. So in this example, everything had a base of 2. So we're going to leave all of our answers in base 2. So we know that our common ratio is 2 to the 4th by the recursive formula. And we know that our starting a sub 1 is 2 to the 3rd. So to put that in an explicit formula, we're going to say a sub n equals a, which is 2 to the 3rd, times r, which is 2 to the 4th, raised to the n minus 1. Well, here we're going to need to use some properties of exponents in order to simplify, because we can't really leave this like this. So we're going to write a sub n equals 2 to the 3rd times, raising a power to a power means we're going to multiply, 2 to the 4n minus 4. And now since we're multiplying exponents with the same base, this is going to be 2 to the 3 plus 4n minus 4. Well, 3 plus 4n minus 4 is 2 to the 4n minus 1. So our explicit formula is a sub n equals 2 to the 4n minus 1. And so to find a sub 9, we're going to do 2 to the 4 times 9 minus 1, which is 2 to the 36 minus 1. So a sub 9 equals 2 to the 35th. And so we can leave it like that because our sequence is in base 2. Let's do one more example. So let's say we have this sequence, and we did this before, so we know a sub 1 is 1/10, and then the common ratio is -2. So to write the equation, we have a sub n equals a, which is 1/10, times -2 to the n minus 1. So there's our explicit formula. We can't simplify that any further. And so to find a sub 9, we're going to take 1/10 times -2 to the 9 minus 1, right? Because 9 is n equals 9. And so really a sub 9 is 1/10 -2 to the 8th. And we know that -2 to the 8th power, since that's an even power, is going to be positive 256. And so a to the 9th is going to be 25.6. And that makes sense because all of our even terms here, right, the first term and the third term are all positive, and the 9th term is also positive. Okay, go ahead and try these. Pause the video. Welcome back. So here are your explicit formulas that you had used from previous examples. Pause the video if that helps you get a little bit further. And here are the answers for the explicit definitions and the 8th term in the sequence. Okay, so that's about it for geometric sequences. So if you want some more examples, go ahead and watch the more examples video. Go ahead and complete the 6-2 geometric sequences reflection. If you haven't done your Khan Academy for this week, I suggest you take a look at some of the suggestions on the bottom of this page or any of the pages in units 6 or 4. Up next is geometric series. Thank you so much for listening.